Hi folks, so we will continue our discussion of Fourier series. I'm not sure about the amount of material we're going to cover in this module. There is more than maybe we can comfortably cover, so I might break this material up into 2 videos. Okay, so let's give it a shot. Let's see how far we can get. So last time we described how to get a Fourier series, and basically what we said is that if I have a signal which is periodic, that is x of t is equal to x of t plus cap t for all t, and then I can define the fundamental frequency in radians per second as 2 pi over cap t, or the fundamental frequency in hertz is equal to 1 over t. And I'll use both of these, and by looking at the units you'll be able to tell whether I'm talking about omega naught or f naught. Okay, and then what we said was we can take x of t and we can write it as a sum of complex exponentials. And these complex exponentials have and in the exponent have n times omega naught, and n goes from minus infinity to infinity, and each of these complex exponentials has a component attached to it, and this component we can obtain by using this integral formulation. We integrate over one period of the periodic function, and this period might be from minus t over 2 to t over 2, or from 0 to t, and that's x of t e to the minus j n omega naught t dt. Right, so that'll give us the coefficients. And the last time what we did was we took a square wave, and which had a duty cycle of 2t0 and the period of cap t. So this is cap t, this was t0 and minus t0, and we came up with the coefficients for this. What I want to do is more explore what these coefficients mean and how we can use the Fourier series to look at functions. So I showed you how to do the computations. The computation is really simple. I mean, you do this integral, and the computation is really not the focus, or really not my focus. How to do integrals and stuff you learned in math class. So what I want to do is more look at what is the physical meaning of these coefficients. Okay, in order to do that, let me try and put this in a slightly more recognizable form. So we'll do this special case first, and then I'll generalize this. So in this special case from the last time, we found that a sub n was equal to a sub minus n. Okay, and so for this case, let's see how we can rewrite this into a form that's more familiar to you. So what I'm going to do is I'll break this up into this summation up into 3 summations. The first one will go from minus infinity to minus 1, and same thing, e to the j n omega naught t. And then I'll have the coefficient for n equals 0 just by itself, and then the coefficients are the terms from n equals 1 to infinity, a sub n e to the j n omega naught t. So I just wrote a0. I didn't write a0 e to the power j 0 omega naught t, because anything to the power 0 is 1, so that's why I'm only left with a0 here. And the last time we saw that this was actually the DC value of the signal. Okay, so what I'm going to do now is I'm going to take this and I'll rewrite it. Instead of making this go from minus infinity to minus 1, I'll take that negative and I'll put it inside. So I'll replace n with minus n, and then I can have n go from 1 to infinity. So this goes summation n equals 1 to infinity of a sub minus n now. So I took that minus and I put it inside, e to the minus j n omega naught t plus, of course, that a sub 0 and plus, and I won't do anything with this. I'll leave that as 1 to infinity a sub n e to the j n omega naught t. Right, so so now what I can do is I can take these two summations and I can put them into one summation. So I'll put this all together. N equals 1 to infinity a sub minus n, I'll put a bracket out here, e to the minus j n omega naught t plus a sub n e to the j n omega naught t, and that's these two summations because both of them are from 1 to infinity, and then I have plus a 0. Okay, now I'm going to use this special case formulation that a sub n is equal to a sub minus n. So let's do that. Let's take that my a sub minus n and replace it with a sub n. So this becomes n equals 1 to infinity a sub n e to the minus j n omega naught t. So all I did was I took this a sub minus n and I replaced it with a sub n plus a sub n e to the j n omega naught t, and then I have the a0 out here. Actually, I'll put the a0 in the front now. a0 plus summation n equals 1 to infinity, and now I'll take this a sub n out in common, and what I'll have left here is e to the minus jn omega naught t plus e to the j n omega naught t. And by this time, you're very, very, very familiar with Euler, so you know that this is just twice cosine n omega naught t. So this is just equal to a sub 0 plus summation n equals 1 to infinity a sub n cosine n omega naught t. Okay, so that's what these, or sorry, 2, because I don't have a 2 down here, so in order to put a 2 down here, I have to multiply this with 2. So here's what we have. So we have a constant term, and we know that this is the DC value, and then we have a sum of sinusoids of frequencies that are integer multiples of the fundamental frequency, right? That's all a Fourier series is. And that's an amazing thing, because it says that even though I can have all kinds of different shapes, in this particular case, my shape is the basic period thing is a pulse. It's just like that. This could be like that. Depending on how badly I want to do integrals, it could be anything you want, any shape you want. And what this says is I can take cosines, which are multiples of the fundamental frequency, and using those cosines, I can reconstruct whatever shape that original signal was just by changing these coefficients. So now what I have is I can take any periodic signal, and instead of worrying about the shape, well, I could worry about the shape, but what I can do is instead of just having this shape to look at, I could then totally forget this function of time, and I could just look at the set of coefficients, and this set of coefficients will tell me what this function should look like. Okay, that's kind of a difficult thing to believe. So I've got a Matlab demo here for you. Let's see if I can make it work. So this is a program that I have, and let me show you what it is. So at the top of this, I've set up T 201 points, and then I have X, which is where my square wave will go, and I have A, where my coefficients will go, And then this is where I'll reconstruct it. This x1 is where I'll put, I'll generate these cosines and weight them with the coefficients, and then I'll add them all together. And I'll show you that as I add more and more terms in, I'll get my square wave back. That's the idea. So the first part of this program, it's just I generate the square wave. This is just to plot. There is no other function for this. And then I use the coefficients that we generated last time. And if you go back to or look in your notes, you'll see these are the Fourier series coefficients. And then what I'll do is I'll regenerate them here. So I'll keep adding coefficients depending on how many coefficients I've decided at the very beginning. So up top here, I decide how many coefficients I want. Okay, so let's try it. Start with 1, and let's run this. And if we run this, we'll find that, and I have to do this in 2 different windows because this is what I get. So if I have just one coefficient, as you would expect, right? I mean, if you look at this thing, if I only have one coefficient, then all I have is a0 plus 2 times a1. And I think a1 was 1 over pi. So 2 over pi times cosine of omega naught t. And omega naught in this case, I've picked a time period of cap t of 1. So omega naught is just 2 pi. Right? So that's all I have in here when I look at this reconstruction with just one coefficient. So let me go back and let me change the number of coefficients. And remember that a1 was equal to 1 over pi, a2 was 0. So upping it to 2 coefficients isn't going to help. So I'll up it up to 3 coefficients. And so let's go back to this program and let's change this to 3. And if you now run this program, and now let me go back to the other, I find that now it is, I have because now I have both the first coefficient and the third coefficient, you can see that adding those 2 cosines up is bringing me closer to this square wave. Okay, if I go back now and make this higher, let me just pick a number, so say 8. And we'll run it again. So I've changed this to 8. And now I'm going to run it one more time. And I get something which is closer to the square wave. And the thing is, as I increase the number of coefficients, I keep increasing the number of coefficients, I'll keep coming closer and closer to the square wave. So let me make this so that it's much more. So let's go back to the Matlab. And let's make this, 50. So now I have 50 coefficients. The sum goes from n equals 1 to 50, still not infinity, but 50. And now we'll try and run this. And we get this. As you can see, I'm coming closer and closer to the square wave. The place where I have, where I'm getting some issues is right at the edges. And if you think about it, now here's something. When we talk about frequency, and we'll often talk about frequency, what frequency is a measure of how fast a signal is changing. So when we talk about a high frequency signal, that means a signal that is changing very rapidly with time. When we talk about a low frequency signal, it means a signal that is changing slowly with time. Another way of measuring rate of change is derivative. So derivative, speed of how fast things change, and frequency, all three of them are saying the same thing. So whenever somebody talks about high frequency, it's just he's talking about a signal whose derivatives are really high, or a signal which is changing very fast. Saying any one of those three gives you exactly the same result. Okay, so now let's take a look at then this result that we have here with 50 components. And what you'll see is that the hardest place that this Fourier series is having to try and approximate is right where there's a transition between the positive and the negative square wave, right? I mean, it's actually a square wave that's been raised up, so it's going between 0 and 1. But, you know, the transition between 1 and 0 is what is the most difficult to capture. And if you think in terms of derivatives, that makes sense, because the derivative at those transitions is actually infinity. So those are the places where I'll really need the high frequency components, right? The low frequency components are pretty good at mapping or at approximating the places in the signal where the signal isn't changing very fast. But in order to approximate, or in order to represent the part of the signal that is changing very rapidly, I need those high frequency coefficients. And if I don't have them, then I get a situation like this, where I have these kind of peaks at these transitions. This is a very common thing. It's called the Gibbs Effect. And you will see it whenever you have fast changes. You will have a problem unless you have those high frequency coefficients available. And you can see this in a different place as well. Now, when you look at an image, you know, if you look at a picture, say, here's my hand, the place where the borders of the hand are, the fingers here, the borders are delineated. These are the edges. And these are the places where the pixel values are changing very rapidly. So I go from not finger to finger. That means that the color is changing quite a bit from not finger to finger, right? But as I go across the finger, the color is about the same. So the pixel values are about the same. When you take an image and you compress it using JPEG, the way that compression works is that image is transformed using a variation of what we're doing right now of the Fourier series. So you get a large number of coefficients. And then because most of the times you don't need those high frequency coefficients, those get thrown away. And that's how you get compression. But the problem is that at the edges, you do need those high frequency coefficients, right? So if you take a JPEG image and you save it with a very low quality factor, that means it'll throw away more and more of the high frequency stuff. And then take a look at the reconstructed image, you'll find that the edges of the image are blurred. It looks like a blurred image because the edges are not as clear as before. So that's what a high frequency is, a place where something changes very rapidly. Okay. So what I'm going to do is I'll put this, let me do just one more. Let me change this to, and I wish I didn't have so many screens, but I don't know how else to do this. So let me change this from 50 to 100. So now I have 100 coefficients. Let's see how that works. And let's go back to Matlab. And there we go. It seems like it's doing a pretty good job of matching the edges. It actually isn't, because I only have, I have very few time points. So I'm not, this is kind of misleading. But in any way, it looks like it's doing a better job of matching the square wave, right? Okay. So what I'm going to do is I'm going to put this program up on Canvas, and you can play with it if you want. I hope you will, because it will help you understand what coefficients are and what the Fourier series is about. Let's go back to our playing around with the coefficients. So we said this was a special case, right? We had this special case where a sub n was equal to a sub minus n. So when does this special case happen? Well, it turns out that it happens when x of t is even. And we can show that pretty easily. And let me very rapidly show that. So a sub n is equal to 1 over t integral over t x of t e to the minus jn omega naught t, right? So assume x of t is even. When x of t is even, x of t is equal to x of minus t, right? So what I can do is I can just take this and replace x of t with x of minus t, right? Because it's an even function. And now what I can do is I can use that variable substitution thing. It's a little bit more complicated when it comes to integrals, but I'm going to kind of skip that and just show you the end result. So if I do a variable substitution, basically I replace minus t with t here, so I'll replace minus t with t here. That'll affect dt as well, but I'll take care of that by playing with the limits. And so just assume that I've done a variable substitution successfully. And now I have, instead of minus t, I have t. So this is x of t. So if I take this minus t and replace it by t, I'll take this minus t and replace it by t as well. So this becomes e to the jn omega naught t dt. And that's equal to 1 over t integral over t of x of t. I can write this as e to the minus j and bring another minus in here. Right? When we do these, when we look at generating the Fourier series coefficients, this n is what this is, right? So here I have minus n, so this will be equal to a sub minus n. So if x of t is equal to x of minus t, then I can show that a sub n is equal to a sub minus n. Okay. If I have an odd function, I can also show, so this is for x of t even. And for x of t odd, I can show that a sub n is equal to minus a sub minus n. Okay, for x of t odd. I've shown it in the notes, so you can take a look at it there. Same kind of idea. Instead of replacing x of t with x of minus t, I replaced x of t with minus x of minus t, and that minus sign went out, and everything else worked exactly the same way, and I ended up with minus a sub minus n. Okay, so there's that. One other thing, let's look at this in a slightly different way. So if I have x, or rather let's look at a sub n. A sub n is equal to 1 over t integral x of t e to the minus j n omega naught t dt. And this time what I'm going to do is I'm not going to use an arbitrary period. I'll use the period from minus t over 2 to t over 2. It's easier to show it this way. So now what I'm going to do is I'll use Euler, and I'll write that as a cosine and sine. So this is equal to 1 over t integral from minus t over 2 to t over 2 x of t times, and this is cosine of n omega naught t minus j sine of n omega naught t dt. So that's equal to 1 over t integral from minus t over 2 to t over 2 x of t cosine n omega naught t dt minus j times 1 over t integral from minus t over 2 to t over 2 x of t sine n omega naught t dt. Right. Now let's take a look at what happens when x of t is even. When x of t is even, then this function is even, and this function is even, and so this product is an even function, right? However, here, this function is even, and this is odd, right? So an even times an odd function gives you an odd function, and if I take any odd function and integrate it over symmetric interval, then I get 0, right? If I take an odd function, which sine is, for example, and I try to integrate it, I'll get a negative area and a positive area, and I'll cancel out, and I get 0 for the integral, right? So if x of t is even, then this will be equal to minus t over 2 to t over 2 x of t cosine of n omega naught t dt. So this was for a sub n, and if I had a sub minus n, I would get cosine of minus n omega naught t, but cosine of minus n is equal to cosine of n, so a sub n and a sub minus n would have exactly the same expression. Okay, there's one other thing I want you to see. If x of t is real, then this whole thing is real as well. So if x of t is real and even, then a sub n is real and an even function of n. What happens if x of t is odd? If x of t was odd, then this would be odd times even. So this would be an odd function. So this would go to 0. And this would be odd times odd. So this would be an even function. And so this would not go to 0. And now what you would get is if x of t was real, then a sub n is a purely imaginary odd function of n, which is kind of weird. Okay, so enough about the coefficients in terms of their peculiarities about even and odd. Let's take a case where things are neither even nor odd, right? So let me take, see how are we doing time. Just one other thing. So let me take just this one thing, and then I think I'm going to break this up into 2 videos. So what I'm going to do is I'll take my original square wave and I'll shift it. So now I'm going to do it something like this, where I no longer have an even function. Okay, and so let's suppose this was minus, what should I do? Let's say this was minus t0 over 2, and this was 3t0 over 2. And again, this is t, and this is a periodic function. It's a periodic function, but it's no longer even, so it's kind of unbalanced. Okay, let's take a look at what the what we get as far as the coefficients are concerned. Okay. So we have a sub n is equal to, again, we'll take the integral from minus t over 2 to t over 2 of x of t e to the minus jn omega naught t dt. Now, here's minus t over 2. If this is t, then minus t over 2 is somewhere over here. Minus t over 2 is somewhere over here. So minus t over 2 to minus t0 over 2, I just get 0. Then from minus t0 over 2 to 3t0 over 2, I get 1. X of t is 1 in this region, so I'll get 1 times e to the minus jn omega naught t. And from 3t0 to t over 2, I again get 0. So if I break this up into these 3 intervals, The only interval that will give me a non-zero value is the interval from minus t0 over 2 to 3t0 over 2. So I can write this as integral from minus t0 over 2 to 3t0 over 2 x of t e to the minus jn omega naught t dt. Okay. So, and in this area, this is equal to 1. So this will become integral from minus t0 over 2. And there's that 1 over t out front that I keep forgetting. To 3t0 over 2 e to the minus j n omega naught t dt. So that's equal to minus 1 over, there's a t from here, and j n omega naught from here. So I'll write that as j n omega naught. And then I'll have e to the minus j n omega naught t evaluated between minus t0 over 2 to 3 t0 over 2. Or, and there was that t that I always forget, so that there's that there. And now what I can do is I can write this as minus 1 over jn, and omega naught I can write that as 2 pi over cap t times t, and then I can evaluate this. So e to the minus jn omega naught, and the upper limit is 3t0 over 2 minus e to the minus jn omega naught, and the lower limit is minus t0 over 2, so that minus will go up here, and I have t0 over 2. Right? These t's cancel out. And now I'm going to use a trick. So the trick is this. What I want to do is take something out from here such that I can take something common from these two, such that the exponent of this is e to the minus something, and the exponent of this is e to the plus the same thing. Okay. And what I'm going to take out is minus j n omega naught t naught over 2. Okay, so let me show you. So this is equal to minus 1 over j n 2 pi. And then I'm going to take out e to the minus jn omega naught t naught over 2. So here I need to have, in order to make the exponent of this and the exponent of this sum up to 3t naught over 2, I need e to the minus jn omega naught t naught. Right? If I multiply these two, the exponents add. Right? When the exponents add, I'll get e to the minus jn omega naught, and then I'll get t naught over 2 plus t naught, which gives me 3t naught over 2. Right? And now I'll do the same thing here. Now here, I want to end up with t naught over 2 plus t naught over 2. Right? So this is plus here. So I want to end up with plus t naught over 2. I have a minus t naught over 2 here. So in order to make the sum of this plus whatever I put in here plus t naught over 2, this has to be t naught, because minus t naught over 2 plus t naught gives me plus t naught over 2. So this is e to the jn omega naught t naught. This is a very, very handy trick. It comes in handy in all kinds of different places. Okay, so now what I'm going to do is I'm going to take this minus inside, so that'll flip these two around, and I'm going to take that 2j inside as well. So now this is 1 over n pi e to the minus jn omega naught t naught over 2, and then inside I get e to the jn omega naught t naught minus e to the minus jn omega naught t naught over, and I took that 2j inside, 2j. And that's just sine. So I have e to the minus jn omega naught t naught over 2. And now I have sine of n omega naught t naught, which is this thing, divided by n pi. So that shift that we did in the time domain, we shifted this thing by t naught over 2. It was over here it was from minus t naught to plus t naught. We shifted it over so that by t naught over 2, so that now I have this goes from minus t naught over 2 to plus t naught 3 t naught over 2. What the effect of that was to introduce this additional phase term into the coefficient. Okay, and this phase term, if I went back and now tried to rewrite my exponential Fourier series in terms of a cosine, what you would get is, and I show this in the notes, what you end up with is this. Let me get a different piece of paper. What you'll get is x of t will be equal to summation, the DC coefficient is still there, and then you'll get n equals 1 to infinity, and you'll get not exactly an, but something derived from an, so let's call it alpha n. You'll get cosine n omega naught, and then you'll get t minus t naught over 2. So you'll get this. When I shifted that square wave in the time domain, what I end up in the frequency domain is a phase shift. So a delay in the time domain is phase shift in the frequency domain. Whenever we talk about a phase shift, we're talking about a delay. So it's the same thing, just like we said, derivative, change, rate of change, frequency are several different words that in the end lead to the same physical thing. When you talk about delay or phase change, they mean exactly the same thing. They point to the same physical thing that's going on. Okay? And that's kind of what you see here. And you notice that the coefficient that we found, a sub n, no longer have that nice property of being even or odd or anything of that nature, right? So the coefficient that we got for this, because it has this nice little even part here, but now it's being multiplied by this complex exponential that makes it each of the coefficients complex. And when this complex part translates when we go back and actually find it in terms of a sinusoid, it translates into a phase shift when we write it as a sum of sinusoids. Okay, so my voice is going, and I doubt if your concentration is keeping up. So I'm going to stop here for this one. What did we do today? We showed that if x of t is, first of all, we showed that these coefficients, a sub n, are really the frequency components of a signal. So what we did was we took, this is some function that's derived from a sub n. So when we talk about like the a1 component, that corresponds to the frequency component at omega naught. When we talk about a2, that's the frequency component at 2 omega naught. When we talk about a3, that's the frequency component. These aren't just numbers. They are frequency components of the signal. And we went through that Matlab code where we actually generated each of the frequency components and then we added them back together in order to reconstruct the square wave. Okay, so that's the very first thing, and that's the most important thing, because I'm going to keep harassing you about this. Then what did we do? We said, well, if we have here some properties, I suppose. If x of t is even, then a sub n is equal to a sub minus n. We said if x of t is odd, then a sub n is equal to minus a sub minus n, right? And then we said if x of t is real and even, then a sub n is real and even. And if x of t is real and odd, a sub n is purely imaginary. No real part. And odd. And then we went through this thing where we took a time shift and we showed that that corresponds to a phase shift. Okay, and that's pretty much it. Okay, and we'll continue with this next time.